Hello everyone, welcome back. Uh, in the last lecture, we were discussing about artifact, ecofact. So these are the evidences which our archaeologists rely on reconstructing the cultural history of the past. So if you are comfortable with what an artifact is, ecofact, fossil, and the features are. Then we had a brief discussion about the identification of site. So, what are all the techniques which our archaeologists are using in identifying a site? Pedestrian survey. Then there are few techniques which we have borrowed from exploration geology, like using the soil interface radar or the ground penetrating radar. Then we also use geomagnetics for this purpose. Correct? Then we just started discussing about uh, dating the evidence. Dating the evidence. There are two types actually, two general ways by which we do it. One is relative dating, another one is absolute dating, which is also called as chronometric dating. We have discussed two important techniques in relative dating. One is stratigraphy. In stratigraphy, I also gave you one concept of indicator fossils. One second. Hope you will not forget these indicator fossils. Indicator fossils, right? These are animals or this may even be plants. These are the plants or animals which lived only for a brief period, not for a very long period. It lived for a short span of time, and either it might have become extinct altogether, or it might have got evolved into some other form, some other form. I told you one example, straight-tusked elephants, which lived during the Pleistocene period. We call it as a Pleistocene megafauna. So these indicator fossils, right, these are used in stratigraphy to find or to establish the relative age of two fossils. Okay. Then we discussed about FUN trio, fluorine, uranium, and nitrogen trio. Then keep that in mind. We cannot use this technique to date two fossils which are separated by a greater distance. Suppose if both the fossils lie 10 kilometers away from each other. We cannot use this trio, you cannot use this method to establish the relative date of the two fossils, because the fluorine and uranium content in the fossil depends upon the fluorine and the uranium present in the given environment. If more is the content of fluorine and uranium, more fluorine, more the same will be deposited or absorbed in a greater amount in the given fossil. Okay. So FUN trio, we generally use it to date two fossils which lie close to each other. Then we have just started, we just started discussing the absolute dating or chronometric methods, in which we just discussed about radiocarbon dating. 14C. So we know how 14C are synthesized in our atmosphere. 14C, an isotope of carbon, right, is not found naturally. These are produced in the atmosphere due to a cosmic reaction, due to an interaction of 14N with the solar photons. This produces this radioactive form of carbon, which is absorbed by the plants. From the plants, it moves into animals. And once when an animal dies, it can no more take this C14, 14C. The 14C decomposes at a known rate. This we can utilize in identifying the age of a fossil. Correct? Okay. So, in the last class we discussed in length that how many beta rays a fresh C14 emits. A fresh C14, right, it emits 15 beta radiations per minute. At its half-life, it emits 15 beta radiation in 2 minutes. So this technique or this can be used to age or used to date a fossil which is not more than 50,000 years. It's not more than 50,000 years. Okay. So I hope you are comfortable with the one technique. So generally, right, they will not ask us to write any particular technique. Generally, right, they will ask us to write any two absolute dating techniques. But once in the past, they have asked us to write about one, that is radiocarbon dating alone. There are a number of techniques. I will discuss few important techniques, not every single technique. Okay. Next important technique is thermoluminescence dating. Thermoluminescence dating. So, what is thermoluminescence? I hope most of you might not have seen or used vessels made out of mud pot, matka, or mud pot or mud pan to cook. Once I was in a tribal hamlet. I was camping there for a week, and food to me was provided by the local tribal people. Some primitive tribes they were in Kerala, and they prepared meat for me. After eating that, right, I asked them what are all the ingredients they are adding. It is not more than what we add in our kitchen, but still, the taste was really something so great. I just asked them how you are getting such a fantastic taste. That was because of cooking in that mud pan or matka. They have a mud pan in which, right, they use wooden logs for cooking. So this mud vessel, right? In a mud vessel, the heat spreads uniformly. And even when they put off the fire, right, the heat dies out uniformly. They say it is because of this, the way in which the food gets cooked is altogether different, and that's why we get this taste. I said this message to my wife. Within a week, right, I could see a number of mud pans in my home, and she started cooking in this mud vessel. And few of our servants, they were breaking their head because it is really very difficult to clean it. And once, right, okay. So if you buy a new mud vessel, many a times you can see when you just keep it immediately over the fire, some microscopic spots will come out of that, chick, 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 like this. Very microscopic lights. Okay. So here, these are thermoluminescence. Thermoluminescence. See what exactly happens when one ceramic object, just forget all those story, now come back to our topic. Suppose our prehistoric man, some 20,000 years ago, if he made a ceramic, if he made a pot, and it got buried in the soil and it is lying there inside the soil for close to around 20 years, 20,000 years, 20,000 years. There will be some radioactive materials in this environment. So as a result, right, because of in microscopic traces at least. So because of these radioactive substances, right, the sum of free moving some electrons, the negatively charged electrons, right, it will be moving freely. These electrons, right, gets trapped in the crystal structure of the atoms of the molecules of this pot. They get trapped. So these free electrons, though they get trapped here, they do not form a part of any atoms or molecule. These are free electrons. Once when we unearth this, once when we bring it up, and in this process, and the process of thermoluminescence, once when we heat this pot is out for after excavation, we are going to study how old this is. So what they will do, they will heat this pot. Even before it becomes red hot, we can see some sparks coming out of that. Generally, these are microscopic sparks actually. These are nothing but once when we heat this, first the free electrons here, right, the free electrons which are trapped here in crystal structure, this will get eliminated. This will get eliminated. And this gives that microscopic spots. And it is not always possible for us to observe and estimate how much thermoluminescence is created by heating. But there are a number of instruments which we use to study or to estimate the amount of thermoluminescence that light emitted. Thermoluminescence. So once when they estimate, okay, it managed to produce some 5 units of thermoluminescence. Then what they will do, they will compare this with the radioactive substance present in this environment. So in this environment, how much free electrons are moving? So this much radioactive substance are here. They compare it. Because with the passage of time, uniformly more and more electrons get trapped. So more the electrons are trapped, more will be the age, and by comparing it with the radioactive substance present in the environment, accurately they can give you what exactly is the age of this artifact. This is called as thermoluminescence dating. So what do you mean thermoluminescence? The thermoluminescence are created due to the displacement of free electrons which were trapped in the crystal structure of these artifacts. Crystal structure of the artifacts. So these free electrons, from the radioactive materials may get trapped here. With the passage of time, more and more electrons may get trapped. And more the thermoluminescence, more will be the age, but still we need to compare that with the quantum of the radioactive materials present in the environment so that we can estimate the age of this artifact. But one problem here is we cannot use this technique to find the age of a fossil, because in most of the fossils, right, we'll find only a bone, only bones. Here we are using heat, right? We are using heat. And if we expose this bone to a heat, it will get charred. So we cannot use this technique, or see, the thermoluminescence dating can be used only to date artifacts, the ceramics, the stone bricks, etc., which were made by human beings or made by our prehistoric men. We cannot use this technique, use this method to date fossils. But even our fossils, right, they trap this free electron. So any object which lies buried in the earth are capable of absorbing these free electrons present in the environment. Free electrons present in the environment. Similarly, even a bone, a fossil may trap this free electron. But we cannot use thermoluminescence dating because if you subject this fossil or subject the bone to heat, it may get damaged. It may get charred. It may become ashes. So, but still there is another technique which we can use to estimate the amount of free electrons trapped in the structure. This method is called as electron spin resonance dating. Simply they call it as ESR dating. ESR dating. We use some spectrometers here. We even call it as ESR spectrometry. Hope during your school days in your physics laboratory, but I used a few spectrometer. You may use a spectrometer to study a number of things. You can study UV rays, you can say microwaves. Correct? So here what we are going to do now, there is a fossil bone. This fossil bone, right, this was also buried in the earth for say 30,000 years, 40,000 years, etc. Even this had trapped a number of free electrons from this environment. But we cannot heat it. So what we will do, we will subject this to a varying magnetic field. Magnetic field. So this magnetic field interacts with these free electrons and these are capable of producing some microwaves. These free electrons interacts with the magnetic field and they produce some microwaves. Then we'll be having a good number of spectrometers which will be used to estimate the amount of microwaves produced here. After estimating the amount of microwaves produced here, and by comparing that with the free electrons in that given environment, we can estimate the age of this fossil. Yes, age of this fossil. So in this method, right, as we are not using heat here, this can be used to date even fossils. This electron, spin, resonance dating. I hope you are comfortable with this dating technique. Okay, fine. The next dating technique is paleomagnetic dating. This is a very interesting dating technique. Paleomagnetic dating. In the last lecture, I told you that Earth behaves like a magnet. Earth behaves like a magnet. It is because of the presence of iron and nickel in the core of the Earth. The purest form of iron in the core of the Earth gives magnetic property, gives Earth its magnetic property. So now I told you this is our geographic North Pole, geographic South Pole. Our magnetic North Pole or the North magnetic pole is inclined to an angle, and this is the South magnetic pole. So now this bar magnet's position is like this. I told you that in the interior of the Earth, so core of the Earth, core is again divided into two, outer core and the inner core. The core will be surrounded by mantle and then crust. We know this. In your geography, you might have read that seismology or the study of earthquakes provided a number of ideas about the interior of the Earth. One thing is very clear that the outer core is not in a solid state. The outer core is in a semi-solid state. Outer core. As a result, the inner core, right, the way in which it spins along with the Earth, slightly it varies. As a result, the Earth's magnetic field, right, keeps changing. At some point of time, maybe some 20 million years ago, the North Pole might have been here and the South magnetic pole might have been here. Some 60 million years ago, it might have got completely reversed. Completely reversed. This we call it as reversal of Earth's magnetic field. Reversal of Earth's magnetic field. At Earth, it happens at a very slow rate. It takes close to around 50 to 60 million years. There's one thing I would like to tell you. Most of the content in the internet nowadays, right, it's always better to go by books. If you are not in a position to find something proper in a book, then right now, even in internet, if you search for some material, search for some research articles. Because most of the things that anybody can post anything nowadays, and the amount of scrap materials which we see in internet is really worrisome. It's really creating a lot of worry. In most of the ones that I ask my students to find in internet that how long it takes for Earth to reverse its magnetic field. Few says are 1 million year. Few say 2, 3, 10, 20, 30. No man. It takes close to around 50 to 60 million years for the Earth's magnetic field to get reversed. But in Sun, it happens at a very fast rate. Once in 11 years, the magnetic field of Sun reverses. Once in 11 years. That's why most of these solar phenomena, solar events, right? It occurs in a cycle of 11 years. The solar flares, the coronal mass ejection, everything which comes out of this and the dark spots, its number increases and declines once in 11 years. Okay. So fine now. Are you okay with the shifting position of the magnetic field? Hope you should be comfortable with this. There is a volcano. I hope by this time you should be in a position to name a number of volcanoes. The Circum-Pacific Ring of Fire. At least few important volcanoes. There are few volcanoes which is called as the lighthouse of the Mediterranean. What is that? Stromboli volcano. Hawaiian volcano, Pilean volcano. You should be comfortable with the famous volcanoes. So because of volcanic eruption, lava may flow. And this lava may settle down, producing an igneous rock. Okay. So there is one such phenomena which happened here. This is the hot lava. Now it is in initially it will be in liquid state. While it is in liquid state, there will be a number of magnetic materials here. Magnetic materials. And these materials, right, will be oriented. Suppose if it happened some 20 million years ago. And if the magnetic field, now suppose the magnetic field is like this. Then 20 million years ago, had the magnetic field be like this. Then when this lava is still in liquid state, these magnetic particles, right, will be orienting towards the then Earth's magnetic field. Correct? After some time, the lava will get solidified. And once when a lava gets solidified, after that, is there any possibility for these magnetic particles to change the position? No. Earth's magnetic field may change, but these magnetic particles cannot reorient themselves towards the changing magnetic field. So these magnetic particles here records the age of the rock. You got it? So geologists, right, if they find a fossil lying over this rock, our archaeologists, if they find a fossil here, then what they will do, they will study this rock in which the fossil is found, rock below which the or rock above which the fossil was found. So this rock, right? Okay, like this, right? Then this should be 20 million years old. So the fossil lying above this, right? Even this should have been somewhere around or less than 20 million years old. This cannot be more than 20 million years old. This is one way by which, right, they find archaeologists establish the age of fossils. Are you okay with this thing? Paleomagnetic dating. Paleomagnetic dating. Fine. Using the magnetic, using the shifting magnetic field of the Earth. Paleomagnetic dating. Next we have potassium argon dating. We have uranium series dating, fission track dating. All these are important, but I think I am making things very complex. Because generally, right, they will ask us to write only two or three techniques, and only once, right, they have asked us to write some technique in particular, and they asked only radiocarbon dating. But still, this potassium argon dating, right, is something very important because most of the fossils in East Africa, we discussed about Olduvai Gorge, right? Which lies between Tanzania and Kenya. This was one very important site in Africa where a number of fossils were discovered, and most of the fossils from this site, right, were dated using potassium argon dating techniques. So it is pretty important. At least I will discuss these two techniques. This potassium argon dating and uranium series dating, because this potassium argon dating was used to date the fossils from Africa, and the uranium series from the cave sites in Germany, Scotland, in Hungary, etc. So these two techniques alone I will discuss. Just keep in mind, if you can read this, read this. If it is not possible, by heart it. Even if that is not possible, just leave it. Whichever techniques you find it as easy, right? Just read those things alone. Got it? So next is a potassium argon dating. The most important thing about this is this technique can be used to date fossils which are 5,000 years old and up to 3 billion years old. 3 billion. How old is our Earth? Our Earth itself is roughly around 5 billion years old. 5,000 million or 5 billion years old. This technique, right, can be used to date fossils which are even 3 billion years old. So a very important technique, right? I'll just tell you what exactly we are doing here. Potassium 40K, it decays into 40 argon. Earlier, the first technique, right, radiocarbon dating, I told you that 14C decays at a known rate. At a known rate. It takes close to around 5,730 years. $5,730 for half of the radiocarbon to decay. We have used that technique. Here what happens, 40K, this potassium, right, it decays into 40 argon. And here it decays at a very slow rate. And the half-life of or half of the 40K to decay, it takes close to around 1,330 million years. Million years. But at the same time, right, there are some more drawbacks also in this dating technique, because here we cannot date. Just keep this in mind in this technique. First thing and right in this technique, we cannot date the exact fossil, but we will be dating only the mineral contained in the rock in which the fossil is found. Suppose if there is a rock, a sedimentary rock, in this rock the fossil is found. So you will be dating only the minerals found in the rock, right? So how old the minerals are. Using that, right, we can estimate the age of the fossil here. And there is a prerequisite. What exactly happens? Suppose there is a sedimentary rock and the rock formation is going on. Okay. So during that time, right, if a volcanic event happens here, if a lava flows here, this heat, right, what it will do, it will eliminate all the 40 argon in this place. As I told you, 40K gets converted into 40 argon. A high temperature event like this, right, will eliminate all the 40 argon, leaving behind only 40K. 40K. So, after the volcanic event, once again this 40K will decompose into 40 argon. And if we compare the proportion of 40K and 40 argon in a rock, we can identify when exactly the volcanic event happened and what might have been the age of the minerals here and what might have been the age of the fossil. Right. Suppose if there are 10 units of 40K and 0 units of 40 argon. So this was the time when the volcanic event happened. With the passage of time now, slowly this 40K will decompose to 40 argon. So maybe after 100 million years, we may find here 10 units of 40K and 1 unit of 40 argon. Okay, so using this, right, by comparing the potassium and argon present in the environment, by comparing these, we can estimate the age of the minerals in the rock and ultimately the age of the fossil. So if you are not in a position to understand, you can just follow these steps. First important thing which we need to write is using potassium. So potassium argon dating is a very important technique used to date fossils which are even 3 billion years old, because the half-life of potassium is 1,330 million years. Using this, right, we can date fossils which are even 3 billion years old. Next important thing to write here is, in this technique, we cannot estimate the age of the fossil, but indirectly only we can estimate it. We can estimate only the age of the minerals found in the rock in which the fossil is found. Next important thing you need to write here is, there is a prerequisite for a high temperature event. Which should eliminate all the argon. So that whatever organ present in the rock, right, have been formed after that volcanic eruption. Then by comparing the ratio of 40K with 40 argon, we will be in a position to estimate the age of the mineral contained in the rock, and using that we can estimate the age of the fossil found in that rock. If you do not understand anything, can you by heart these 5 steps and can you write it? The most important thing is this technique is used to date the fossils found in East Africa. East Africa. Potassium argon dating. The next one more dating technique. So with this we'll stop. Okay, I will not discuss even the fission track dating. That's also a bit simple only, but I don't want to complicate the things. So these two techniques are bit these are very complex techniques and hardly there are few laboratories which can deal with these techniques. So we cannot go in depth about the science behind these dating techniques, but at least some idea what exactly we need to know about potassium argon dating. So if they ask you to write about in anthropology, if they ask you to write about potassium argon dating in particular, what are all the things we can write? Okay, maybe we need to write for some 200 words. The first important thing, it's a very important dating technique which can be used to date fossils which are even 3 billion years old. 3 billion to 5,000 years we can date using this technique. And this technique was used to date the fossils discovered from East Africa, most importantly the old white arch. Next thing, this technique cannot be used to estimate the actual age of the fossil, but we can use this technique to estimate only the age of the mineral or how old that rock is, the mineral present in that rock in which the fossil is found. Next important thing is there is a prerequisite for a high temperature event, that is a volcanic eruption. So this is also essential, that is prerequisite for a high temperature event. A high temperature event like volcanic eruption, what it does actually, it eliminates all the 40 argon originally present in the rock. So then now the 40 potassium decays at a known rate. So whatever argon we have found there, we can see in that rock, right, were those which were formed after the volcanic eruption. So using this, right, we can identify when that volcanic eruption happened, how old this rock should be, and how old the fossil it is found in the rock. Got it? So simple. So just write this. This is sufficient. Next is the uranium series dating. Uranium series dating. So this technique, right, can be used to date fossils which are less than 3 lakh years. And this technique was widely used in Europe to date most of the Neanderthal fossils. We have discussed earlier that Neanderthals are also called as cavemen. Most of the Neanderthals lived in caves, largely to protect themselves against the cold weather. Okay. So this technique, right, is used to date fossils which are found in caves having karst topography, or you can simply say limestone formations. limestone formations like stalactite, stalagmites, etc. Have you seen these things? See, these are formed in limestone regions. Suppose if there is a cave, under the earth surface, there is a cave, and if there are some limestone here. So running water, right, will bring down, will melt, or sorry, will dissolve this limestone and bring the water here inside. This water, right, may stand here as a drop. Generally, you can see this in our places after monsoon rain, so during rainfall. So we may have some metal strings meant for drying the cloths. There we can see waters may be standing in drops after rainfall. Or sometimes even in the window shades, sun shades, right? Water may stand like this. After some time, right, this water may, few water may fall down, few may evaporate. And once when they evaporated, we can see some small amount of salt left behind. Here the water contains lot of salt, right? So when it evaporates, it will be leaving lot of salt. And slowly, right, this may accumulate, resulting in the formation of some structures. This water may fall down here. From here also the same thing may happen. So this creates a number of such landforms. The one standing above is called a stalactite. One standing down is called a stalagmite. This may fuse to form cave pillars, and will be having number of dripstones, number of other features which your geography sir will be discussing in your GS geography lectures. In India, we have one such cave in Araku Valley near Visakhapatnam. Araku Valley near Visakhapatnam, limestone caves. Okay, I'll show you one picture of what these stalactites, stalagmites. So this is a limestone cave. Okay, so now what happened? Some maybe some 60,000 years ago, 70,000. See, this process, right? It's a very slow process. It takes a few thousand years, sometimes even a few million years for these limestone structures to form. For these stalactites and stalagmites to develop, right? It may take thousands and thousands of years. Running water contains uranium. Running water contains uranium but not thorium. So if this water or if this running this uranium from or the water, if it gets trapped somewhere, this 235 uranium, right, slowly decays into 235 thorium. 235 thorium. So we might have known about thorium, right? In our three-stage nuclear power program, in the third stage, we are using thorium as a fuel in our nuclear reactors. MOX fuel, mixed oxides of uranium. Okay, fine. And into thorium. So the proportion of 235 uranium and 235 thorium, right, gives us idea about how old these limestones are. Suppose if there is a limestone cave and one stalagmite is just forming, Now one Neanderthal died here, keeping his hand over the stalactite. He died keeping his hand over this stalactite. And slowly the stalactite, right, will continue to form like this. So now what they will do, they will collect the limestones of this region. Okay, and they will study how much 235 uranium is there and how much got decayed into 235 thorium. So with passage of time, suppose if it is fresh, 10 units, there will be 0 units of thorium. Maybe after 10,000 years, right, there may be 9 units, and here it may be 1 unit of thorium. Maybe after 30,000 years, we may see there may be 8 units of uranium and 2 units of thorium. So just by comparing the uranium and the thorium, 235 uranium, 235 uranium and 235 thorium present in the rock here, present in the limestone here, our archaeologists will be in a position to date how old this fossil may be. So remember this technique, right? We can use it to date fossils which are less than 3 million years old. Sorry, not even 3 million, 0.3, just which are 3 lakh, few lakh years old. 3 lakh. We know our Neanderthals, right? They survived in the earth roughly around 60 to 40, 60 to 30 million years. Sorry, 60 to 30,000 years ago. Neanderthals are Homo sapiens sapiens. Okay, Neanderthals are roughly around 50,000 years old. So, this uranium thorium dating technique was used to date the fossils, generally the Neanderthal fossils, which were discovered from the cave sites in Europe, from Germany, Hungary, France, etc. Got it? So we have one more technique, fission track dating. I'm not going to complicate things. See, guys, make yourself comfortable with any two techniques. For example, radiocarbon dating is very, very easy. You can make yourself comfortable with that. Then thermoluminescence dating is also very, very easy. Paleomagnetic dating is very easy. And after that, in particular, why I taught you about the potassium argon dating and this uranium thorium uranium dating is these techniques were used to date few very important fossils. For example, the potassium argon dating was used to date the fossils from East Africa, from the Old White Gorge. And this uranium thorium dating was used to date the fossils from Europe, the Neanderthal fossils. It is for that reason sometimes they may even ask you to write indirectly. The very important technique used to, very important dating techniques used to date, which was used to date Neanderthal fossils. They may ask you to write about the technique used to date the fossils, which was used to date the fossils from East Africa. These are the ways by which, right, we can expect our examiner to make a tough paper. So it is for this reason alone, right, I took some pain to teach even the potassium argon dating and the uranium series dating. Okay. So if you can just remember some 2 or 3 techniques, that is sufficient. Got it? Okay then. Fine. So now this is sufficient about the principles in prehistoric archaeology, and now let us continue our discussion in the cultural evolution. Paleolithic, Mesolithic, Neolithic, Chalcolithic, Copper Bronze, Iron Age, etc.